The other big technique for error recovery in recursive descent LL1 parsers is the so-called Pascal technique. And it's called the Pascal technique because it was first introduced in the classic Pascal P-machine compiler from ETH. But it isn't restricted merely to Pascal. It can work for any recursive descent compiler or any recursive descent parser, I suppose, more accurately. And it relies on two basic observations about a well-formed program. So if you have a well-formed program, then on entry to any parsing procedure, which allows the non-terminal capital A to be replaced by the sentential form alpha, the look-ahead at that point must be an element of the predict set of that production. And then on exit from the procedure, the look-ahead should be an element of the follow set of the left-hand side of the production. In other words, follow A. So this suggests a technique for error recovery, which is to synchronize at the start point and the exit point of every parsing procedure. So the basic idea is that at the entry point to the routine parse A to alpha, we will check that the look-ahead is an element of the appropriate predict set for the production. And if it isn't, we will start to skip tokens until we arrive at something that is such an element. And then on the exit point, we will check that the look-ahead is in fact an element of something that can follow this procedure. So now we're down here. And once again, if it isn't, we'll start skipping until we find something that is. So Pascal error recovery then is using the entry and exit points of each production for error resynchronization. And there is no error recovery at all in the accept routine. Instead, it is distributed throughout the parser. So this is, in some sense, almost the polar opposite of the S-algol technique. In the S-algol technique, all of the error detection and recovery was concentrated in the accept routine, and there is no other error recovery code anywhere else in the parser, which is very nice because it means you don't clutter up the parser with lots and lots of error recovery code. On the other hand, in the Pascal technique, the accept routine basically just prints an error message if the current token is not equal to the expected token and continues. Otherwise, it just advances the look-ahead pointer, but it doesn't do any error recovery. Instead, the error recovery in the pure Pascal technique is distributed throughout the parser. Basically, it's a number of error recovery calls in every parsing production. So we could think of something like this. This is actually a pretty good technique for dealing with extra tokens. So if the extra tokens occur at the start of the piece of the input that's being passed by production, then we can loop until we see something that is one of those. So it's good for dealing with extra tokens in the input. Once again, it displays this sort of opposite behavior or polar opposite behavior to the S-algol technique. So S-algol is good for omitted symbols and is only mediocre at extra symbols, whereas it turns out that the Pascal technique is pretty good for extra symbols, but kind of mediocre for omitted symbols, and so has to be fixed up to deal with those. So anyway, we'd have code then at the start of our parsing routine, parse A to alpha, that looks like this. First of all, we'd have a check, and we print a syntax error if there was some sort of problem, okay? So if the current token.code is not an element of the predict set, then we print out a syntax error. And then we would loop until we see something that is an element of the predict set, eating up the input until we've arrived at that production. If you want to implement that, of course, you usually don't have something like, is an element of. We don't have an inbuilt set type in C. So instead, I have an implementation of such a set type, and it's implemented in the library, and the header is in sets.h. So the function prototype is in sets.h, so you'd have to include that if you want to use this inset routine. And then there's actually another version of syntax error, which takes an entire set of elements as its first argument, and it takes the symbol we've actually got as the second argument. So the original syntax error just took expected token, current token. This one is a set of expected symbols at this point. So if we're not in the set of predicting symbols, which here is called predict set, it's a global, then we report an error message, and then we loop until we see something like that. So this works very well if you have this sort of situation here. So you see this grammar here, S maps onto capital A followed by terminal E, and A is either a D or it's a recursive version of itself fronted by a terminal A, B, or C. So essentially, the thing that can start this, so we're in parse S, and we want to call parse A. We call parse A, and the predict set of parse A, of course, at this point is A, B, C, or D. So when we're in parse A, we will then look at the input and say the input looks like that. So we have W, X, Y, Z, P, Q, or A. So the parsing procedure for A will clearly cycle over all the extra symbols in the input, all of this stuff, and it'll resynchronize there. But think about what happens if the input does not actually contain an element of predict, the predict set of this production. Now we have to call this production. Okay, it's obligatory here. So parse S is going to have to call parse A. But say it calls parse A and we have something in the input that looks like this. And this is actually the follower of A. So if the input does not contain an element of the predict set, the routine will ignore the entire input or potentially resynchronize incorrectly. So you have this sort of issue here. So clearly what we have isn't adequate. So instead of just synchronizing on the predict set of the production, we also have to synchronize on the follow set of the left-hand side of the production. So we have to add this in here as well. Notice that we only produce the error message if the current look-ahead symbol is not an element of the predict set of the production. But we have to loop while we're not seeing the predict set or the follow set of the left-hand side, which would get turned into code that looks something like this in practice. It's a lot less elegant, I suppose. Now, at that point, it means that we might actually have synchronized on something which is not actually an element of the right-hand side of this production. You see it here. So we need to make sure that we only execute the code for the production if we've actually synchronized on an element of the right-hand side of the production. And the original code to do the parsing A to alpha or right-hand side is all in here. So this is like boilerplate code at the front, and then we have this here. And of course, we have the fact that this could cause syntax errors as well. So we have to make sure that on exit, we resynchronize with the follow set of the left-hand side of the production. So first of all, we have an error message generator here like this, and then we have a loop so that we loop until we see something that is an element of the follow set of A. And of course, in practice, we'd have to augment that with the end of input symbol as well to make sure that the loop stops at some point if we run out of input. Now, all of this, you can see it here, this and this is so-called boilerplate code because you have to basically put something like this and something like this into every one of the productions that parses a non-terminal symbol. So that's a lot of extra code in your parser. It works reasonably well where the amount of source code to be parsed by any one production is small. Essentially, it works well for pure BNF, but it has problems if you have missing followers of productions. They can cause very large amounts of input to be skipped looking for a resynchronization point. So how do you deal with that? Well, one technique to try and get around that is to use so-called panic mode error recovery. The idea is to have tokens in the set of tokens which are never skipped, the so-called beacon symbols or beacon set. And if the parser sees a beacon in the input and is currently attempting to resynchronize, it always resynchronizes on the beacon. this is generally accepted as quite a crude approach to error handling, so-called panic mode. The hope is here that by resynchronizing like this, we will at least be able to pass some of the remaining source instead of skipping a very large amount of the remaining source program. But unfortunately, on the other hand, it almost never resynchronizes really well. So you tend to get cascading error messages if you have panic mode coming into operation. So a typical beacon symbol then, of course, is the semicolon for the C, Java, Pascal family of languages. Basically, most of the languages around at the moment, with the exception of the Fortran and COBOL. So a few points to then make about the basic Pascal scheme. I've sketched it out very quickly there because I'm not asking you to implement it. This is an important point to realize. I don't want you to attempt to implement the basic Pascal scheme. And the reason is it clutters up your compiler too much. You have too much code to write at the start point and end point of all your parsing productions. It makes the parser very big and very clumsy. Now, some code generators can actually automatically generate this code for you. A good example is the Antler code generator, which will generate Java code to generate a parser, and it can put error recovery routines like this in automatically. It automatically generates the boilerplate code for you. But if you're trying to do it by hand, it's really quite painful. So I'm not asking you to use the Pascal scheme. The other thing I'd like to point out as well is that I've left out some of the fine detail of the Pascal scheme. There are tricks you can use to cut down on the number of sets you need to have, and you can dynamically generate some of the synchronization sets as you run through the parse. And if you're interested in that, you can see the books by Niklaus Wirth on the Pascal P4 compiler, where he explains it quite well. The book by Luton as well, Compiler Construction, also has a good section on Pascal-style error recovery using constructed synchronization sets, but you don't need it for the module. It's only for interest, I suppose. So just to emphasize then, these are the bones of the basic Pascal scheme. I'm not asking you to implement it because it's too big and clumsy to implement for a student compiler. If you were doing a production compiler, you might have to think again, but for a student compiler, I'm not asking you to implement that. Instead, what I would like you to implement for the student compiler, in other words, parser 2 and compiler 1 and compiler 2, is a hybrid technique called the augmented S-algol scheme. So the augmented S-algol scheme basically takes the accept code, which we have for the basic S-algol recovery, and keeps that. So the basic S-algol accept code that I talked about in the previous video, I want you to implement that just as it's written down in the slides. Basically just copy and paste it into your parser. And then I want you to add a modified version of the Pascal scheme applied in a very small number of places in the parser. And these are places where the plain S-algol scheme doesn't perform very well. And this essentially corresponds to eBNF choice points. So the basic S-algol scheme, its big weakness, as we've said already, is that it has the problems at the entry and exit points of eBNF operators. And the big culprit here really is the repetition operator. The point about the eBNF repetition operator is it can encompass a very large amount of the source program, but because of the optional nature of the repetition operator, then you can have a case, and we've already seen this, where accept calls simply don't happen in the error conditions. Instead, we skip past the while loop and we try to resynchronize on what follows the while loop in the parser source code. And that means that you can have a large portion of the program where the basic or plain S-algol technique is not really getting a chance to operate. Basically, because of the while loop sort of structure, you end up with a situation where you're synchronizing on something that appears too late in the program, which can either get you completely out of sync, as we'll see in a moment, or it can mean you skip too much of the input program before you resynchronize. In the previous case, as I showed in the last lecture, we did in fact resynchronize adequately, having skipped quite a small portion of the source, but it doesn't always work in such a friendly way. Let's see an example where things can get much worse. So let's look at this little program here, and I simply have a pair of transposed symbols, but they appear at the start of what is essentially an optional sequence of statements. You can see them here. So what we have is a while statement is a while, Boolean expression, do, block is begin, optional sequence of statements, followed by an end. So once you've seen the begin and committed on it, the only thing you're committed to at that point is the end. So what's the behavior of simple standard salgol when it hits this error? And you may remember I said that there can be problems with transposed symbols. So we run down through this. We're running through pass while statement. We see the except do, sees a begin, okay, throws an error message, and then set skipping mode, comes back up, okay, comes down here, pass block is called. Pass block sees the except begin, which is here, and it clears the skipping mode, and it looks as if everything's worked really well, okay? But it hasn't. The reason it hasn't is we've virtually inserted this do, and then we've resynchronized on the begin, which is, really nice. But unfortunately, the do, the transpose do, which was in the input, it hasn't been lost. It hasn't been skipped. It's still there. So what happens now is we see the do. We generate, what do we generate here? We generate an error message at this point saying, I've got a do, but what did I expect at this point? Well, I've just inserted a begin, and the only thing that must follow a begin is an end. So pure salgol virtually inserts this and enters skipping mode looking for something that must follow an end, which is either a semicolon or an end of program marker or an else keyword. And it finds a semicolon and resynchronizes there. So you might say that's not too bad, but the problem is that a real begin in the source has been balanced with a virtual end. So the begin-end pairing of the program has been lost, the program has become unbalanced, and the pass will terminate early. So we can see this happening here. We virtually inserted this end, which matched against this real begin in the source program. Okay, we had an error message there, and then we started skipping, resynchronized on this, okay, saw the do, generated an error message, inserted a virtual end at that point, and then entered skipping mode looking for something we can resynchronize on after the end, arrive here, and then we start passing again, and that's fine, and then we see this end, but the program now thinks that this end belongs with the outermost begin in the program, and we essentially stop passing at this point. In fact, what will happen is you'll get another error message at this point saying, I expected to see an end of program marker, and so on. So you get early termination with, in this case, a small error cascade. You've certainly got an error. You've got an error cascade appearing here. You get a mysterious do, end expected got do at that point, whereas you've already got a begin expected got do over here, and then down here you've got, oh, that's not too good. I got a semicolon. I expect to see an end of program marker, this full stop here. So the pass stops there, and you get lots of extra error messages. So how could you fix that? Well, this only happens in this case because pure salgol can't synchronize with one of the things that starts a block, because the eBNF operator is implemented by a while loop, and the while loop doesn't see anything that looks like the first set of statement when you have an error condition here. Okay, so if you look down what's happening here, at this point, the pass at the start of the eBNF repetition operator, and what it sees in the input is a do, and it says, okay, that's not an identifier while, if, read, or write, so it skips the while loop. And then the only thing that must follow the while loop is the accept end, so you get the virtual insertion of the end, and basically the bad behavior we've seen already. So how do you get around that? Well, if you realize that at this point, because we've just started an eBNF repetition operator, we could synchronize on the thing that starts a statement. In other words, an identifier, a while, an if, a read, or a write. And what have we got here? We've got a write, so we could synchronize on that. And then we'd have essentially fixed the problem for this case. And the idea here is, with augmented S-algol error recovery, is to do exactly that. Look for important eBNF operators in your program that are responsible for potentially large amounts of source text and forced resynchronization at those points. So you're getting a sort of Pascal-style resynchronization built into the program at the eBNF operators. So for example, for this repetition operator inside pass block, I would put a synchronize call before the while so that I would check to see whether I have something that looks like the sort of thing that could start a statement. And then, of course, I have to remember that there might be no statement at all there, in which case I'd have to make sure to include the thing that could follow the optional block, which is an end. So I'd have synchronize on. Well, what should I synchronize on? I should synchronize on the first set of statement augmented with the thing that could follow a statement. Essentially, we're synchronizing on this sentential form here. And this sentential form, the repetition operator followed by the end, can start with anything that starts a statement and also an end. So we'll have the first set of statement in here augmented with the thing that can follow the repetition operator, in other words, the end here. And then, of course, we'd want to have some emergency resynchronization points. So we'd have some followers and beacon symbols in here. And these would represent good resynchronizations, and these would represent inferior kind of emergency resynchronizations. Working out this set is easy. Working out this set tends to be a bit of trial and error, because if you put too many things in there, you get bad resynchronizations. If you don't put in enough, you get bad resynchronizations, and so on and so forth. So it's a bit of a black art determining what should go in there. Whereas this is pretty straightforward. The synchronized routine, as I write it, it accepts pointers to sets. Okay, so these are sets, statement fs underscore aug, and statement follow beacon symbol. Okay, and I'm passing in pointers to them here. We'll see that in a moment. That's just for efficiency. And then we fall through to the standard code. So we've synchronized, and then we check to see whether we're in the first set of statement. And if we are, we call pass statement, and then we accept the semicolon, and then we're at the bottom of the while loop. So we have to synchronize again with exactly the same call. Synchronize on the entry and synchronize on the exit of the while loop. And it has to be before we actually exit the while loop. It has to be actually the very last statement or piece of code in the while loop just before the closing bracket. So the same thing happens again. And then we fall through here to the accept end. So what's in this synchronized code? Well, it's essentially the Pascal code, Pascal error recovery boiled off into a single routine, okay? Essentially. So the first thing that we pass in is a pointer to the augmented first set of resynchronization symbols. These represent essentially good resynchronization points. And then we have an emergency set of so-called follow and beacon symbols. And this is as I've said, this set has to be sort of worked out by trial and error for any particular grammar, and getting it right is more an art than a science. I don't actually expect you to work it out. I will give you what I found to be good sets to do this, okay? These are easy to do. So what do we do here? If we are in the set, the F set, okay, then everything is great. If we're not, we have to start resynchronizing. So we print out a syntax error using syntax error 2, saying we wanted something in this set, we got that. And then we loop. What do we loop on? Well, we loop until we see something that's either in this set or this set. I've just put them together here using a routine from sets.h called union. Union takes two, it's a var args C call. So the first parameter is the number of arguments that follow. So here we have 2 arguments, because you can take the union of many sets using union, but here we only have 2. So F and follower, and first and follower and beacons. You then obviously have to set up these synchronization sets, okay? So you need a routine which is called before the parse starts, which sets up a whole bunch of global sets, which you use for your resynchronizations, okay? These are the arguments passed in to synchronize at the various points in the parser where you call synchronize. I've shown two of them here. This is the setup for the augmented first set of statement, which is the first set of statement plus end. Now, the first set of statement, which you should be able to work out, but you don't even need to because I'm telling you what it is identifier, while, if, read, and write. And the augmentation is the end keyword. So we have these symbols, these token codes we want to put in there: identifier, while, if, read, write, and end. There are 6 of them. So the first argument to init set is a pointer to the set you want to initialize. And the second argument is a count of the number of token symbols you want to put in there. Here we have 6 of them: 1, 2, 3, 4, 5, 6. So this second argument must be 6. Okay, and don't get that wrong, because if you do, you can get strange behavior from the C code. And we want, well, what do we want for the follower and beacon symbols at this point? Well, this turns out to be, this is a sensible set of them: semicolon, else, end of program, and end of input. It's very important to include end of input in all of these follower and beacon symbol sets, just to make sure that if you have run out of input, then the thing stops. It doesn't just loop forever, reading in end of input tokens and saying, that's not something I want to synchronize on. Okay, so if you find that your parser is hanging, you may have left out an end of input in one of your follow beacon sets. And again, you take as an argument to init set, well, a pointer to the set you are trying to initialize, which is in statement FBS, which is a global set object that you have declared earlier, okay? And this call, setup sets, happens before the parser starts off. So this happens, this is called from main, and before the parser starts off, you initialize all these sets. And there are 4 of these, so the second argument to init set in this call is 4 for this 1, 2, 3, 4 different token codes. This set is justified on slide 29, or at least shown on slide 29, and so is this one. You also need sets for the other primary augmented S-algol resynchronization points. I haven't shown them in here, but they're the same sorts of things. So what are these resynchronization points? Okay, so let's just look at the grammar of the language for the moment. And the grammar for the language looks like this. I have it here, and let me blow that up. Yeah, and on the next slide. Okay, so these are all the productions in the language: program, declarations, procedure declaration, parameter list, formal parameter, block, statement, and so on. All of these down here, okay? And some of those don't need any sort of augmented S-algol resynchronization. Look at assignment. It starts with a terminal token. Clearly, you know, that's going to call accept assignment at this point. So, you know, ordinary S-algol is going to do fine. Similarly for procedure call list at the start of it, and so on. Okay, and we work our way down here. Down at the very bottom of the grammar, there are 1, 2, 3, 4, 7 productions, starting with variable and including var or procedure name, identifier, integer constant, alpha num, alpha, and digit. You do not write, and I should emphasize this, you do not write parser productions for these. You don't have any parse identifier in your code. You could have a parse variable, but you probably don't need it. You don't have any parse int const or parse alpha num or parse alpha or parse digit, because all of this stuff describes the so-called microgrammar of the language. And this is the stuff that's basically handled for you by the scanner. So the scanner can generate tokens for integer constants. So it can assemble an integer constant by itself. It doesn't need to know the grammar. And it can also assemble identifiers for you automatically. Okay? So you don't need to have parser routines for these. And strictly speaking, these two here, you could have parser routines for them, but all they would do is call accept identifier. So you don't really need parser routines for these two either. So the things in light blue here, these are the so-called microgrammar productions of the grammar, and they are not implemented typically in the parser. Certainly in your case, you would not attempt to implement this, or this, because these are provided for you through the scanner, which can return an identifier or an integer constant token. And you can choose whether or not to implement these two. I normally don't bother because they don't do very much, but that's completely up to you. Apart from that, what I've shown here is I've shown the primary and secondary augmented S-algol resynchronization points in the language. The primary augmented S-algol points are shown in blue, and the secondaries are shown in green. And you only have to, in parser 2, you only have to implement augmented S-algol resynchronization for the 3 primaries. In other words, you need to have augmented S-algol resynchronization in program, parse program, in parse procedure, and in parse block. You do not need to include augmented S-algol resynchronization in parse declarations or parse procedure declaration or parse formal parameter or parse procedure call list or any of the others. You can if you like, but you don't actually get any marks for it, so I wouldn't waste my time. The reason for this is that the primary or blue points are parts of the grammar that control potentially very large amounts of the source. So resynchronization is important in these places. The green ones really just improve the quality of error reporting to the user, but they don't do that much for resynchronization, so you don't really need them. You would have them in a production compiler, obviously, but you don't need them for your student compiler. So let's look at an example. So there's the rest of them. These are, you can see you have more secondary points here. And once again, I don't actually require you to implement augmented S-algol resynchronization for these secondaries. You can if you like, but there are no marks for it. So let's look at the 3 primary augmented S-algol resynchronization points and how we should synchronize on them. Well, look at the production for a program. So it's a program is a program keyword followed by an identifier followed by a semicolon followed by an optional declarations block. This is something that starts with var. Declarations start with the keyword var. And then followed by 0 or more procedure declarations, which start with the keyword procedure. So I want you to implement augmented S-algol resynchronization for parse program, and you need to do that in 3 places. You will have 3 calls to synchronize inside parse program. One at this point, which will synchronize on a first set here, which consists of var, procedure, and begin. These are all the things that can start a sentential form that starts at this point. So you either have a sentential form starting with a var keyword because you have declarations there, or you have a sentential form starting with a procedure keyword because you have no declarations, but you have a procedure declaration. That's perfectly legal. Might be unusual, but it's legal. Or you have neither declaration of variables, globals in this case, or procedures, but you have to have a block. So at this point, the things that can appear at this synchronization point, the first set of the sentential form from this point on to the end is var, procedure, and begin. And at this point and this point, the things you can see are procedure, because you might see a procedure declaration appearing here, or there might be no procedure declaration, or you might be here and there might be another procedure declaration, so you see procedure, or there might be no more procedure declarations, so you see what follows procedure, which is a block, so procedure and begin. And then the follow set of this structure here is essentially the end of program marker. So if we think of this as being the sentential form from here to here, then what can follow it is the end of program marker, the full stop. And then useful beacons here. Well, the obligatory, really important beacon end of input. That should appear in every one of your follow beacon sets. Well, you'll only have 3 of them, but it should be in each one of them, just to make sure that you don't loop forever looking for something which isn't the end of input if you start to see end of input. And end, the keyword end, turns out to be another useful beacon. It'll give you some resynchronization, probably not brilliant. You can fiddle with the contents of the follower beacon set, but I find that this is a fairly stable one, which doesn't generate, it gives you reasonable resynchronization in panic mode cases without generating too much cascade, although it's impossible to avoid cascades completely. And here's what the code would look like for that then. So here we have parse program, program, identifier, semicolon, accept program, accept identifier, accept semicolon. Then we have our first synchronization point. So synchronize with the first set number 1, okay, which we have here as being this lot, and the followers and beacons, which we have from here as being the union of these two. Okay, and then we have the synchronize in front of the while loop, synchronizing on first set 2 on the same followers and beacons. And then we have synchronize at the exit of the while loop, again on the first set 2 and the followers and beacons. Then we call parse block, accept end of program, accept end of input, and we're done. Then we have procedure declaration, which looks very similar, okay, because a procedure starts with an identifier, followed by an optional parameter list, followed by a semicolon, followed by the bit that I want you to deal with, the declaration section, followed by the optional nested procedure declaration section, followed by the obligatory block, followed by the semicolon that ends this. So I found that the appropriate synchronization first set at this point is var, procedure, and begin. And you should be able to work out where that comes from. It's pretty obvious. The first set at this point is procedure and begin. Again, it's pretty obvious where that comes from. And then you want beacons, okay, followers and beacons, and the end of input marker, end of program marker, and end. Now you might say, why isn't the semicolon included in there? Because that's actually a follower of all this lot. Well, I've experimented with using that in the past, and I found that it's better to leave it out because it causes too many poor resynchronizations. Okay, so that's kind of a rule of thumb, a bit of black art there, just from experience playing with this. So I wouldn't recommend that you include the semicolon in the follower beacons there, even though it strictly is a follower. However, it's up to you, but I wouldn't put it in if I were you. And then we have the block, which we've seen already, with the augmented version of the first set of statement. You think of this is the first set essentially of the sentential form extending from here to here, including the end, which is why the end is in there. So it's the first set of statement plus the end. The useful beacon, of course, in this case is end of input, and followers in this case are end of program, semicolon, or else. So I put end of program, semicolon, else, and end of input into the follow beacon set for that lot. And then finally, this is an example of a secondary synchronization set, procedure call list, which is pretty straightforward. As you can see here, you don't need to implement this or any of the other secondary salgol points. So just to emphasize, what I would like you to do for parser 2 is I would like you to implement primary salgol resynchronization inside accept, and then the 3 secondary or the 3 augmented salgol primary resynchronization points. Okay, so there's basically 2 parts to your parser 2. First of all, you include code inside accept, and then you include, as well as that, you include the 3 augmented salgol synchronization points, and that's your parser 2.